Welcome to AIT YouTube channel. Myself Syed, Assistant Professor, Department of Chemistry. Today we will discuss about the colorimetry. It comes under fifth module, instrumentation. Thereby we will try to discuss about the principal, instrumentation and applications of colorimetry. So first come across the introduction, where basically it is a spectroscopic tool which is based on the interaction of highly energetic electromagnetic radiations with the matter. That means it's all about the interaction of light with the matter. Say it's an analytical tool. Specifically the colorimetry comes under absorption, spectroscopy, and thereby the frequency range is 400 to 760 nanometer. And the most important thing is it is applicable only for the colored sample, hence it is known as colorimetry. So now come towards this the basic principle involved in the working of this colorimetric spectroscopic tool. The fundamental basic principle is Beer's and Lambert's law. This colorimetry works on the basis of Beer's and Lambert's law, which states that when a beam of monochromatic light interacts with the analyzing sample, so the extent of absorption capacity of analyte is directly related to the concentration of the medium as well as path length of the medium. It means when a beam of monochromatic light interacts with the test solution, say capacity of absorption by analyte is directly related to the concentration as well as thickness or path length of the medium. See here, say the absorption capacity of an analyte or a substance where is directly related to the concentration as well as thickness of the medium, and this is the Beer's and Lambert's law, where when the intensity of incident light interacts with the sample, so the part of light is get transmitted out, part of light is get reflected, and reflected light is negligible one, and the part of light is get absorbed by the medium. See here, absorption equals epsilon Ct, where epsilon is the molar extension coefficient, T is the thickness of the medium, and concentration, it is C is the concentration of the medium. Now come towards the instrumentation. See here, basically in the block diagram it consists of the source of light, then the filter or monochromator, then sample holder with the cuvette, then detector or photocell, amplifier, and finally output to display the final concentration. See, now the first component, the source of light. Usually the tungsten filament lamp is used as a source of light in the colorimetric tool, which is passed through the filters or monochromators, which filters all the other radiations and emitted the single beam of light which is required to interact with the matter, and the filtration can be achieved by means of the filters or monochromators. Cuvette sample, the analyte have to take in the cuvette, and which is placed in the sample holder, where the monochromatic light interacts with the sample which is taken in the cuvette, and especially it is made up of either the special glass or plastic or quartz material. And the shape of this cuvette is either maybe it is square, rectangular or round shape, which is with the fixed diameter, usually it is 1 centimeter, and having the uniform surface. After that, the detectors or photocell, where the main function of the detector is to detect the intensity of the light which is converted into the electrical signal, which is finally amplified by the amplifier and finally recorded as an output. Now come towards the basic applications. Basically it is widely used in the food industries and used in paints and textile industries for the analysis, and used in the analysis of the biochemical samples. Advantages, the most important thing is it is an inexpensive and very well applicable for the quantitative analysis of the colored solutions, and least quantity, that is minimum quantity of the sample is required for the analysis, and its transportation and handling is easy. And come towards the disadvantages, limitations of this colorimetry. It is not applicable for the colorless solution. As I told you in the beginning itself, it is applicable only for the colored solution. Hence, it is not applicable for colorless solutions. And it does not work in UV or IR region. It is not possible to set a specific wavelength. And whatever we are setting the lambda max, we have to carry it, that is the standard parameter. And the wavelength, instead, we can set the range at the parameter. That is, we can't set the specific wavelength, the exact wavelength for the analysis. But instead of that, the range of the wavelength we have to set, which has a parameter. And similar colors from the interfering substances can produce the error, deviation from the actual results. Now they come across this colorimetric estimation of copper. This is a basic example of the colorimetry where the copper will be estimated by means of colorimetric tool. So thereby the first procedure, so take the different concentrations, say for example 5, 10, 15, 20, 25 cc of copper sulfate solution in 5 to 6 different volumetric flasks, 50 cc volumetric flask, and add 5 cc of ammonia for all the flasks and dilute it up to the mark by using ion exchange water. In the same way, prepare the blank or reference solution by taking just ammonia and make up to the mark, which is used to set 0 at the standard reading, 0, and measure the absorbance of each solution at 620 nanometer for the specific color, and tabulate the reading and plot the calibration curve between the absorbance or optical density versus copper sulfate solution. The conduction of the experiment, I'll show you, just watch it.